Hello. Yeah, the mic works. Coffee was okay, I hope. I had cold water, it was great. Next up, gravitational waves. I know nothing about that stuff, so I'm really excited myself. Please give it up for Ivan and Volkan.
Hey, hey. Hello, everyone. First of all, I do want to state that before starting, I do have a big respect for you because I'm seeing like really brave-hearted people filling up this room. You know why you are brave-hearted? Because you are right now here, even though you sucked at physics at the college. You know what? How do I know that? Because I'm one of you too. But for some reason, there is an inexplicable seduction that we have from all these sci-fi mambo-jumbo. Like we are following, I don't know, astronauts on Twitter, or watching sci-fi movies and reading about NASA conspiracy theories. So that is great. And you know, we will give you what you are looking for. We will make you sure that you understand what gravitational waves are at the end of this presentation in such a form that 5-tweet long chain. And another statement that I also want to do, which is off topic by the way, actually Yuri tried to mention about it. This is a historical moment in the history of Bol.com. I think this is an historical moment in the history of Spaces Summit as well, because like this is the second time we are holding a summit which is called Spaces, and there were no presentation about space at all. All right, let's face it, this is shame. All right, this is shame, and we will really be so. Right now, Ivan and I will be sacrificing our souls in the gods of ITMT, so thou shalt learn about gravitational waves. All right? So, oh, I need a clicker, I suppose. Yeah, okay. So first of all, I will start with the motivation, because I don't have anything to do with physics. My PhD is not from physics, so I will be trying to motivate you about the subject, like why should you care at all? And why does the gravitational waves matter at all? I mean, apart from that. Then, in the preceding part of the presentation, Ivan, who actually holds a PhD in physics and is to blame for is to blame for any kind of inaccuracy in this presentation. So he will really start talking about space-time, gravity, and blah blah blah. And it's also highly likely that at the end of the presentation you still won't be understanding anything. So we held a frequently asked questions session. I will be asking stupid questions to myself, and I will be answering them again in the same stupid manner. But again, this is a presentation for you. This is not a presentation for the sake of making a presentation. If you do not understand anything, let us know. Shout, all right? You can interrupt. All right. Is this working at all?
Should be.
Okay. Okay, why should you care? I will start with making an analogy. All right, this is a timeline. And this is where the Christ born. So, just make sure. So, like almost 3,000 years before the birth of Christ, ancient Egyptians knew that when they touch to electric fish, they were getting shocked. Like there was something going on wrong with that fish. They knew that. And then, like almost 2,000 years later, then think like 2,000 years later. Can you imagine that? I'm talking about 2,000 years later. So 2,000 years later, the first guy started really conducting experiments with it. But look at the experiments. Touching a cat's fur with a rod of amber. So this is the science back then. And then like a couple of thousands of years later again, so this is the William Gilbert who coined the term electricity that we know of today. Many people actually think electricity is a scientific work, but look at this, it has nothing to do with science. It means of amber. And then a couple of hundreds of years later, there was a guy who is called Ebenezer Kinnersley, demonstrated that when you heat a wire, it shines, all right? By the way, this has nothing to do with the gravitational waves. I mean, electricity has nothing to do with the gravitational waves. But this has something to do with the moment that we are living in right now. This is Amsterdam in the 18th century. The thing that I like about this image is that, like, you can also observe the technological advancement back then. You weren't able to see any steam engines over here. Like, there was no electricity or whatsoever. And you see this guy? He's trying to explain something to the fellas over here. And this is me. So, and I'm saying, now I will heat this wire and it will start shining. And the guy next to that is saying, Goed verhaal. But this is exactly what is happening right now when you think about it. I'm telling you, there is something called gravitational waves. This is exactly what is happening. I'm telling you, there is something called gravitational waves. Again, but why does gravitational waves matter? All right. I suppose many of you have seen this image. This is what we call as the observable universe. In the middle of it, this is our home sweet home. This is the Milky Way, and in that Milky Way, we have the solar system. In the solar system, we have the planet Earth. All right? And we call this giant black sphere observable universe, and this is the limit. Like, you have seen this image before, I suppose, in the newspapers, magazines, I don't know, in the Twitter, Facebook, somewhere around on the internet. But what is observable? What do we mean exactly by observing? Like, is it just the light? Is it radio waves? I don't know, is it heat? Is it sound? I had the same question as you did. So, and I looked at the Wikipedia as a lazy developer, and this was the explanation that I got. The observable universe, blah, 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 blah. If you're not Ivan, you probably won't understand what's this saying. So, then I tried to, also since I was a programmer, I tried to debug it. So, okay, it's a spherical region of the universe comprising all matter. This I can understand. Fine, so far so good. It's observed from Earth, and at the present time. So I'm observing it right now. But the most important thing, which I try to underline, highlight with the green, is I'm observing it using the electromagnetic radiation. So what I do mean by observance is the electromagnetic radiation that has been sourced from the limit of that giant ball. And it radiates back and reaches to me, billions and billions and billions light years away. Then this makes me question, is this the only way I can observe the universe? Is there just electromagnetic radiation? Isn't there any other ways that I can do it? And again, I went to Wikipedia, and I searched for radiation. Radiation is the emission or transmission of energy. Fine. What kind of radiations are there? One of them is acoustic radiation, like ultrasound, sound, or as you can imagine, this depends on the physical medium. Like, is it underwater? Is it using the air? Is it in the vacuum space, like in the space? There is electromagnetic radiation. This is radio waves, microwaves, visible light, X-rays. Actually, these are all, for instance, your microwave at home or the light that you see, they are all different forms of electromagnetic waves. There is also particle radiation. This is the magic that scientists are doing at CERN, so using those giant particle accelerators, they are trying to observe these kind of radiation. And the fourth one is the gravitational radiation. This is new. This is new. This is something new. But it is also old as well. So how come that it can be new and old? It is old because compared to the other three were actually observed by experiments. Maybe it was a mistake of a scientific experiment that was being conducted. So they were actually, for instance, while looking for particle radiation, they didn't know that they were looking for particle radiation. But gravitational radiation, scientists has been predicting that almost a century ago. Even Einstein was predicting that there is something needs to exist that is called gravitational waves. So this is also really remarkable, like the math told us that needs to exist 100 years ago. But we weren't able to prove it until 2 years ago. And that is what I do mean, but I was that fella in the 18th century picture. So this is I think this is like the moment that we found electricity. Oh, if it works. So when you look at the picture from this side, so what I'm telling you, I'm not telling you we are not living in the world that we are supposed to live in, but there is an analogy between this photo and what I'm trying to tell you, and it is that, like, I'm giving you a new tool that you can observe the universe that you were never ever able to do before. So like, think about, like, you used to be a colorblind person, and I'm telling you, like, right now you will be able to observe the universe with the colors. It is not just around you, it is not just like, it is the entire universe. It's also within the atom too. You don't really need to think far ahead. You can also think inside an atom too. So, this was my part. I tried to cover why should you care and how do gravitational waves matter, but this is actually not what you need. What you need is, what is gravity and what are gravitational waves? And my friend, Ivan will help you with that.
Thanks, Volkan. So, I hope you're not confused by now, because you will be. No, I'm kidding. If you are confused, as he said, stop me.
Yeah.
The point of the talk is for you guys to get an idea about this. Not all the details, but the conceptual ideas. That's what I want to see. So, what is gravity? Now, all of us know the effect of gravity. If we have an apple or something, kind of like Newton did, and it's attached to something, if it's not attached, it's on a height, it'll fall down. And that's the effect of gravity. That's nothing special, we know it's there. But actually, how do we explain gravity? Well, it turns out that gravity is really complicated, and it is hard to explain, but let's try to do it together. Now, the person who so far gave us the best explanation of gravity is Einstein. He said, time, space, and gravitation have no separate existence from matter. Basically, this means that all of these four concepts are tightly linked to each other. And the first part of that is time and space. When we talk about gravity, we always talk about something called space-time. Now, this concept was actually originally thought of by another scientist called Minkowski, but it doesn't really matter. And the idea is that you cannot observe space and time separately. They are actually always connected via the speed of light. Now, what that has to do with this graph is, if we are in this red spot, this is us now at this moment, and we represent our space, all of our spatial coordinates, as we like to call them, in one dimension, just on this axis, then if we call the other axis time, and we can do that by multiplying time with the speed of light. And this is the main point. The speed of light is the thing that binds time and space together. If you multiply time by the speed of light, you also get a space unit. And the speed of light is a constant finite thing. Even though I still don't see why the hell the speed of light is the constant and it's finite, it is. And basically, anything that happens in the future, which on this graph is just going up, is happening within a certain area called the light cone. So the light cone is an area where any event can be theoretically connected to a different event. And that is because they have to communicate with each other somehow, be at the speed of light, or something slower than the speed of light, but not faster. But don't focus too much on the light cones and all those things. They're super cool, but they're complicated. The idea is that the time and space are one unit. They're one thing together, connected by the speed of light, connected by the fact that the speed of light is a constant thing observed by everybody in the entire universe, always the same. Now, if we take the same two-dimensional picture, the space-time, and we show it as a grid, as a mesh, then we can see what Einstein was talking about when he said mass and gravity and space-time are all connected. He basically said that all these objects, which have different masses, the way they produce gravity is by bending the very space-time around them. So a heavier object bends space-time more than a lighter object. Now, how that translates to gravity, the Earth, for example, the Moon, well, the Earth bends space-time around it. And the Moon is actually trying to go on a straight line, but because the Moon is in this hugely bent space-time around the Earth, the Moon is actually going in circles around the Earth. So that is actually the effect we see from gravity. Those are all the orbits. That's the reason why everything is going in orbits around each other, all the stars and suns. And this has been confirmed experimentally in many, many details. Now, knowing this concept of space-time, knowing the connection between space-time and gravity, how gravity is the effect of bent space-time, we can start talking about some very weird things like black holes, which are my favorite things. And basically, A black hole is so messed up that it actually bends space-time infinitely. Infinitely. So it bends everything to a single point. If the Earth was bent to the size, compressed to the size of a black hole, it would be this big. And all the space-time around it is so bent that actually not even light can escape it. That is where the name black hole comes from. If light was trying to pass this area, the light would just go down, stop existing forever, that's gone. That's why it's a black hole. That's why you can never actually observe a black hole directly through light. But it's also important to take note that if some light beams were to pass somewhere around here, they could still pass. As long as they don't fall into this hole itself, the event horizon, then they can still pass. And now, why am I talking about black holes? Well, they're the place where we will use to study gravitational waves. They are the place where this bending of space-time is so big that the effects of gravitational waves are the largest. So if you want to prove a theory, you want to start somewhere where it's easiest to make an experiment on it. And basically, so to start talking about gravitational waves themselves, we have to define them again from Wikipedia. And again, we have to debug it in Volkan's way. Basically, gravitational waves are the disturbance of the fabric of space-time, and they're generated by accelerating masses, so moving masses, heavy objects that move, like the planets, stars. And this is interesting. They propagate at the speed of light. This was postulated 100 years ago, that this disturbance in gravity and the space-time itself will propagate at the speed of light. Just because the speed of light is a cool constant and it makes sense to call everything speed of light. But we will see later that this was not without basis. Now, let's start visualizing things. This is a black hole merger. This is a simulation of two black holes. As you can see, they're black and they're holes. So nothing special there, right? But when they rotate around each other, something very interesting is happening. You can see, I'll pause it for a second so we can talk about it, that it looks like the stars behind them are dancing, which is completely weird, right? But as we mentioned before, light that doesn't fall in the black hole but passes around the black hole gets bent, because space-time itself is bent because of so much mass and density of the black hole. Now, as the black holes are rotating around each other, they're actually constantly messing around with space-time, and all the light that's passing through is just being messed up. So it looks like those stars behind are dancing and moving around, but they're just where they were. It's just the light in between the stars and us and the black hole gets messed up because of all the space-time bending. And also, these black holes will merge at this point. And at this point, there will be a lot of effects, but of course, everything dies down, and we have a massive black hole in the end. Now, this ties in back. This is a simulation, of course, done by NASA. Who else? And this ties back to Volkan talking about electromagnetic radiation and how we were observing the universe. This was a picture in the electromagnetic spectrum, light, right? We can now look at the exact same thing through a completely different way of looking. This is a simulation, again, because we haven't actually seen this, but it's simulated, of the two black holes rotating around each other, and all of these lines are the gravitational waves. What's being spread out now, the red lines, kind of like if you throw a stone in a pond and some waves start spreading out, the same way gravitational waves bends in space-time itself, the space-time is going shrinking and contracting, are spreading out from this event into space. Of course, in the end, leaving the same one black hole. Now that we've seen these pictures, let's take a look at how the scientists actually measured this event. Basically, this was done by the LIGO experiment, Laser Interferometer Gravitational Wave Observatory. This is an experiment in the United States, and the experiment has been constructed 40 years ago, but it took them 40 years to actually get it running. And the idea behind the experiment is, I think, beautifully simple. There is an event, such as a black hole merger, that generates a lot of gravitational waves. The experiment itself only has two long tunnels, 4 kilometers each. The tunnels are exactly the same length. Exactly the same length, this is really important. And they're 4 kilometers long because we want to see the effects of space-time itself being bent as it's passing by through these tunnels. And these effects are, of course, very, very small. They're 10 to the power of minus 30 something meters, so it's really nothing. Okay, maybe not minus 30 something, I'm exaggerating, but they're very small. And now we can see in detail how they did it, schematically as well. This is also cool. They had two exact copies of the same experiment. So one is, they're both in the United States. They're 3,000 kilometers away from each other. The idea is that if you have two experiments doing exactly the same thing at exactly the same time, you can confirm those results, right? I mean, you cannot just claim that you've measured gravitational waves. This way, they have two experiments exactly the same, confirming the results. And each of these experiments has these two tunnels. Now, let's take a look at schematically what they do with these tunnels. Why do they need the tunnels? What's going on? Basically, they have a laser beam. They have a laser beam that goes along the tunnels. It gets reflected back with mirrors, and it's joined back in the beginning and set up so that if the tunnels have exactly the same length, 4 kilometers, as they do, as you would expect, then nothing happens, because the laser is so set up that the signals from the lasers are exactly opposite to each other, so they just cancel. So in a normal situation where everything is fine, there's no signal here. But if there's an event like a black hole merger, for example, then gravitational waves are passing by, and they're bending everything. They're distorting space-time itself. And because of this, the tunnels change ever so slightly in dimension, ever so slightly, but enough. Enough so we can detect it. Enough so there is a signal. And the moment we have a signal, we know there was a gravitational wave. Now you can, in the next slide, you can actually see the result, the actual plot, the graph that was shown. And basically, let's skip. Yeah. So these are the two black holes. And take note, they're 30 times the mass of the sun, 29 and 36 times the mass of the sun. This is the signal. So ideally, this signal down here would be just a flat line. But these are real experimental conditions. And I can tell you as an experimentalist, these are things that are extremely boring and are the reason some people leave science. But they take 40 years, and they're very important. And if you do not have these types of signals telling you that this is roughly the zero, then you cannot claim anything real. And then you see it here, this moment, where there are different signals, that this is the moment that actually corresponds to the moment when these two black holes merge. And this is the moment where 3 times the mass of the sun, I'll repeat that, 3 times the mass of the sun is released into space. This insane amount of energy that I cannot even comprehend bends space-time itself. By the way, this was 1.8 billion light years away. So that's also, I mean, fucked up. I mean, I cannot use a different word for it. It's just so far away, you cannot imagine it. And also the energy itself is just so big, but we measured it. Because with using a very simple thing, 2 tunnels, right? They just change distances. But I mean, this was a work of 40 years, I don't know how many scientists. And finally, we show what can also be measured with gravitational waves. This is a neutron star merger. Now, this video is slightly nicer, it has music. And this is an event where 2 neutron stars rotate around each other. They also produce gravitational waves, these blue lines. But what makes them different between black holes is that when they merge, they explode. They create heavy elements, gamma rays, light rays, everything. And we can also measure that at the same time as the gravitational waves. So there is a huge explosion, very short explosion, but we can measure this. And basically what happened was, when this event occurred, the 2 neutron star merger, an experiment called the Fermi Experiment, it's a gamma ray telescope, so in the electromagnetic ray spectrum, detected, let me just pause it for a second. It detected an event, and it knew that it was roughly in this region of the sky. But then another experiment, the integral, said it was in this region of the sky as well. So they were overlapping here, and then the gravitational experiments also detected the same experiment, the same event. It's gonna happen, yes. And then they said it was either here or here, but this part corresponded with this region of the sky. And then the Virgo from Italy, also gravitational wave experiment, confirmed it was in this region. And then 70 other observatories from I don't know how many astronomers zoomed in, look at all of these events and tried to see if any of these events fit, and it was this event. So this was, they realized that this bright spot here, which nobody was paying attention to, was actually a neutron star merger. And they measured it at the same time with gravitational waves. Actually, the gravitational waves arrived just a bit earlier than the gamma rays. which proved that gravitational waves also travel at the speed of light. Something that they predicted 100 years ago, you know, with math. And it was correct. So yeah.
All right.
Now, finally,
I
we
think
can just talk about...
We have 2 minutes, so I will try to walk over the frequently asked questions as fast as possible. Can we travel or absorb faster than the speed of light? Not according to, not to the best of our knowledge, and this wasn't also predicted up until at least right now by math. So does this enable teleportation? No. Can we beat gravity?
Maybe? I don't know.
Maybe.
I don't think so, but maybe.
Yeah. Nothing is saying it's not possible. Can I experience this myself? Yes, I want to do this stupid experiment right now. Yes, right now, I'm creating a gravitational wave. So, and do you still recommend? Yeah, I do definitely recommend you to watch Interstellar, so it still makes sense. So, please go ahead. We are running a little bit out of the... 1 minute. Yeah.
No, that's exactly correct. It's part of it. So as they're rotating around each other and generating the waves are also energy, right? So any energy leaving the system slows down those two things. Yeah, exactly. And then they're slowing down, collapsing, and also the gravity itself is pulling them in. But yeah, that is the main reason.
Next. Yeah.
Yeah.
Does the length of the tunnels also change the accuracy of the readings?
It does, exactly. So ideally, you would have a 100-kilometer long tunnel, but that brings a host of other problems, of course. That's the percentage that you're looking at. So larger the tunnel, easier to see. Yeah, Jonathan?
Aren't there so many events in the universe in general that thing goes off all the time?
Yeah, that would be nice, but no.
No, but and also that is the reason it took 40 years to calibrate those results.
It's part of the reason. I mean, it's just super sensitive, and people spend their entire lives on chasing -5. Yeah, sorry, I have a thing against
Yeah,
people
I think we are being thrown out, right?
Yep, time's up.
Yeah,
Guys,
all
give
right.
it up for Ivan.
Woo!